Hi everyone, we've just got everyone entering right now from the lobby, so we'll just give it a minute or so until that activity has stopped. There we go. As we're getting some last minute people joining, I just wanted to say welcome to those who couldn't join our morning session today, and welcome back for those who did join our morning session today. Welcome to the Ambition Surgery for Spring Accelerator 4, all about emerging contaminants. And this session, whereas the morning session was more of a context setting type of session, this afternoon session is more of a deeper exploration. But if you did miss this morning session, we did record it, and we're recording this session as well, and we'll be sending both of those and the slides out following this afternoon's webinar. So first up, I would please like to introduce you or reintroduce you to Thomas Walker, who's the Senior Innovation Manager here at Spring. So again, Thomas leads the innovation program at Spring, overseeing the accelerator and the development of Spring's innovation offering. He's the perfect person to be speaking to us today all about this event, why we're here, and an introduction to the Ambition Surgery. Over to Thomas.
Thanks, Natalie. Hello, everybody. Good afternoon. As Natalie's saying, welcome to the kind of second half of the Spring Accelerator for Ambition Surgery. As a reminder, Ambition Surgeries are our launch events for Accelerator programs. So this is, I guess, the official launch of Spring Accelerator 4, focusing on a challenge inside Water Innovation Strategy Theme 2, providing clean water for all. And again, specifically, we're looking at emerging contaminants. My name's Thomas. And similar to this morning session, I'm going to do a short introduction, well, a shorter introduction than this morning, just for those of you who were here already. And then before handing back over to Natalie, the amazing speakers, and then popping up a little bit once or twice throughout the day. So Spring. Spring is an innovation accelerator that enables collaboration within and beyond the water sector to drive transformational innovation. Now, instead of going through a full introduction again, I will just remind you all that fundamentally we exist as Spring to increase collaboration, reduce duplication, and accelerate learning in the UK and Ireland water sector. And we have kind of two main parts of our business that help us do this. We have a knowledge transfer side where we host other events called showcases, which are sort of 2-hour deep dives into projects to help people learn and accelerate their own efforts in a given space, and have a library of case studies to do something similar. And then we have the innovation side, which at the moment is characterized primarily by the Spring Accelerator, and is the reason that we are all here today. And here we're really looking to increase the collaboration and reduce the duplication of work that the water companies go through specific challenge areas. So speaking to the Spring Accelerator, again, the reason we are here this afternoon, it is an end-to-end challenge process that calls out for specific implementable innovation for water companies to trial, progress, and adopt as a collaborative group. Our goal with the accelerator is to take solutions from wherever they are when they apply to a program to a place they are more market ready. Getting multiple water companies involved in the process and the projects, so they split costs, share learnings, and the project in question happens fewer times across the sector. I spoke, to the process in more detail in this morning session, so I won't bore you all again. But everything does kick off with our event today, the Ambition Surgery. We invite a great cross-section of the industry together, which is everybody in the room here, to help us articulate our problem area and begin to define the specific challenge the accelerator is going to focus on. Here, we're basically trying to reduce all the duplication of all the work we could possibly do here, bringing together relevant experts to share their insight, go through learnings from historic trials, and again, begin to define what successful resolution looks like. So what are we going to be learning about? What is our challenge area? We are looking at emerging contaminants, which, to us means addressing the knowledge gaps, treatment limitations, and regulatory challenges of often unregulated chemicals and other substances detected in the water and environment that pose potential risk to human and/or ecosystem health. Now, the speakers in this morning session went through in much greater detail on this from a technical point of view, a water company business point of view, and a regulatory one. But really the goal of these presentations and conversations that we're having today are to take our general understanding, take our broad challenge area, and to refine it into something specific and actionable, and ultimately feed into the writing of our call for innovation, which is the challenge that we put out to the world. And this, what's on the screen here, was our was our starting point. So with this starting point, this definition of emerging contaminants, this morning, as I said, we had 4 great speakers giving us the context behind emerging contaminants from a technical, business, and regulatory perspective, and some sort of out-of-sector inspiration from the Spring Accelerator 4 sponsor, RSE. This afternoon, however, we're going to start by learning from things we've already tried in this space. This first section is for some international colleagues of ours to share lessons learned, outline some guardrails, and maybe signal what the challenge shouldn't really focus on, because we don't necessarily want to do stuff that's already been done, right? And then we have a panel session towards the end of the day to begin to outline the playing field, asking the types of things that we need to do to understand, to measure, to actually take meaningful action in this space. Like, where should we focus our efforts? Where should we focus our challenge to create genuine value for the sector and sort of society and the environment writ large? Then we're going to take all the data from today and consolidate it, learn from it, and start building our call for innovation. As I say, it's this call for innovation that we publish as the official challenge. What this does mean is at the end of the session today, we are not expecting a perfect challenge statement. The purpose of this afternoon is for us to have an interesting, productive conversation about our challenge area, about emerging contaminants, getting insight from our expert speakers, creating space for everyone in the room to participate and share their knowledge, and for us to get a little bit excited about the potential for innovation and where the value is to be created. It's going to be a learning day, essentially, a learning day. So as I said, we're going to kick off with 3 international talks. So we're looking at the right-hand side of the screen here. One from the Massachusetts Waterworks Association, so giving us a US perspective. A case study from Xylem on a project they ran in Germany, and learning from a PhD researcher from the University of Antwerp. And then, as I say, we'll close with our great panel session that will help us define some boundaries or goals for our challenge. And yes, we're here, as I say, on the right-hand side in the afternoon session. If you did miss the morning session and would like, that more context and that sort of foundational understanding of our challenge area, as Natalie said, we will be sharing the recordings and the slides after these sessions. So don't worry, you didn't miss out completely. So look, I am really excited about the speakers and the panelists we have for you this afternoon, but it is not all about them. Similar to this morning, we want to hear from everyone in the audience as well. But this time there are 2 ways to do that. First of all, we will have Q&A moments. So please feel free to post your questions in the chat as they come up. The Spring team will collect them and we will feed them to the speakers. So don't feel that you necessarily need to wait for the Q&A sections to post your questions. As I say, we also recognize that the expertise in the room extends beyond those who we've invited to speak. So if and when you want to contribute to the conversation and offer your opinion on one of the topics we're discussing, you can use a Slido dashboard, which I'll demo in just a second, to kind of give us your input and give us your ideas. Then after your session, we take the data from the talks and from what's been input into these survey dashboards, and we'll start to consolidate it and bring together that call for innovation. So once you click on the link in the chat that we will post in just a moment, you will be taken to a screen like this. We have a handful of questions there already, and there's actually going to be pretty much the same questions that we'll be asking throughout this session. So the idea is that you click on one, you'll be taken to Slido relating to the specific question, you type in your answer, and you hit send. And look, I can't stress enough, like, we really do value the input of the wider group. So please add your thoughts, your ideas, your challenges to any of the directions outlined by one of the Spring team or by one of our speakers today, because it'll help us a lot in crafting that call for innovation that is, relevant and valuable for you and the sector writ large. I think with that, I am going to pass back to Natalie to start to introduce our next section and speakers. As I say, I'll pop up once or twice throughout the rest of the event. So see you all very soon. Thanks, guys.
Thank you very much for your presentation, Thomas. What a great overview into the work that we're doing. And just a reminder, to complete that survey is your opportunity to contribute to what the call for innovation is going to be looking like. So off the back of the work from today, the survey questions that you answer, that's going to go into producing some research questions that are going to go back to all the different water companies in the UK and Ireland to decide what direction that they want the call for innovation to take. So it's not just a survey to ask you how the event's gone today. It's super, super important if you'd like your contribution to go forward into the call for innovation that we're going to be preparing around this topic. So thanks very much for that, Thomas. So our next section today is all going to be about an international perspective to the topic of emerging contaminants. So we've got 3 10-minute presentations, followed by a collective 5-minute Q&A after all 3 speakers have done their talks. So I'd like to welcome Jennifer to come along and share her slides and turn on her video while I do her intro. So Jennifer Pedersen is the Executive Director at the American Waterworks Association. So she's the Executive Director of the Massachusetts Waterworks Association, which is a non-profit membership organisation dedicated to the advancement of the drinking water profession. For approximately the last 8 years, Jennifer has been helping Massachusetts public water systems navigate the world of emerging contaminants, specifically PFAS regulation. She says, in her own words, it has been a wild ride, and she's looking forward to sharing some of those insights with you today. So thanks very much, and welcome, Jennifer.
Thank you, Natalie, and thank you for having me. I will start with just a brief overview of my presentation today. So we will be talking a little bit about the regulatory landscape in the United States and specifically in Massachusetts. This is an area that we've been concentrating on a lot over the past decade. We're going to talk about the water system concerns that we've faced during the regulatory process, the costs, the regulatory activity, legislative actions, and legal actions. So as Natalie said, we are a nonprofit Mass Waterworks Association. We are based right outside of Boston. We have 1,500 members across the state of Massachusetts, dealing with all aspects of water. We are a small staff, and we have a lot of volunteer committees, and we participate a lot of state work groups to share our expertise. I just want to set the stage a little bit for what we consider a public water system in the US. So it's at least 15 service connections or serving at least 25 people for 60 days of the year. Drinking water standards apply to water systems differently based on the type of water system. So we are dealing a lot with community systems, so those serving an entire town, but there are also, smaller public water systems, non-transient, non-community systems. So condo associations would be a community system, but a non-transient, non-community water system would be a school. A transient, non-community water system would be a restaurant. So it's important to know this context because the regulations apply differently to these different water systems. As a speaker said this morning, water systems are highly regulated. That is the case in the United States as well. We must comply with federal and state drinking water standards. So in the United States, we have a law called the Safe Drinking Water Act. It applies to all public water systems. It was passed by Congress in 1974 to protect drinking water quality. It has been updated several times since 1974 to add new areas of concern. It does have the United States Environmental Protection Agency as our top regulator of standards. And in the United States, most states have delegation from the US EPA to implement the Safe Drinking Water Act at a state level. It's important to note that the federal standards have to be followed. The states can be more stringent than the federal standards, and we will see that as we go into the conversation about PFAS. In Massachusetts, the Safe Drinking Water Act is implemented by the Massachusetts Department of Environmental Protection. And I've put on the side of the slide sort of the various regulatory efforts that our public water systems are facing. Emerging contaminants is a broad category, and so I've highlighted a couple others that we are dealing with in Massachusetts and in the United States, such as manganese and pharmaceutical products, but we will concentrate today mostly on PFAS. There was a slide this morning that showed this. I'm just going to put it up here for a quick review that PFAS is everywhere in the environment. It's coming from a lot of different sources. It is obviously a man-made contaminant. And in the United States, PFOS was phased out of production, and PFOA was also voluntarily phased out. It still can be imported, but it is important to note that since the phase out of PFOA and PFOS, we have seen blood levels decline in the US population. So that's good news that once it was phased out, there isn't as much exposure. In Massachusetts, we've had testing in place for a number of years. So this is a quick map of Massachusetts to show the areas of detection of PFAS based on the different size water systems. The green are those community systems, those municipal systems. So the Safe Drinking Water Act process takes some time. And because of that time, many states have felt the pressure to act sooner. So EPA has a rule called the Unregulated Contaminant Monitoring Rule. Back in 2013, they asked public water systems across the United States to begin testing for PFAS. As someone said this morning, when you begin to test, you begin to find. And so they sort of look at the sample results and occurrence to determine how they're going to regulate contaminants going forward. EPA began being concerned about what they were seeing throughout that testing and announced a health advisory for PFOA and PFOS of 70 parts per trillion or nanograms per liter, which was a non-regulatory, non-enforceable standard. Mass DEP in Massachusetts sought to adopt this as their own standard, also non-regulatory, non-enforceable, but rather than the 2 compounds of PFOA and PFOS, they expanded that to 5 compounds that they felt had similar properties. So in the United States, we have, and specifically in Massachusetts, we have areas where citizens groups can get involved. And in Massachusetts, a group called the Conservation Law Foundation filed a formal petition to Mass DEP to regulate PFAS as a treatment technique. So they felt like there are so many different compounds out there that it's not appropriate just to regulate 5. They wanted to see a treatment technique that would perhaps get as many compounds out of drinking water as possible. Mass DEP had a process. They had public input, stakeholder input. They rejected the treatment technique standard approach, but they did say that they would move towards regulating PFAS with a maximum contaminant level for Massachusetts. So in the meantime, the science had evolved and they began feeling that a lower limit was more protective of public health. In December of 2019, they set a standard of 20 parts per trillion for 6 PFAS compounds as a waste site cleanup standard or groundwater cleanup standard. And then they moved to regulate that same 6 compounds in drinking water with 20 parts per trillion. So that was in October of 2020. We came up with a formal enforceable standard for 6 PFAS compounds at 20 parts per trillion. In 2021, EPA had their next round of unregulated contaminant monitoring rule, so UCMR 5. They adopted that and said, going forward, we're going to expand the number of PFAS we want systems to test for. And so this latest rule, which our water systems are currently in the process of testing from 2023 to 2025, will test for 29 PFAS compounds. In June of 2022, EPA issued interim health advisories for PFOA and PFOS at 4 parts per quadrillion. This was really astounding to public water systems in the United States. This is below the level of analytical quantification. So it created a lot of concern for our public water systems. How are we to even understand what's in our water if we can't even sample to that level? Basically, what EPA was saying with this action is that there is no safe level of PFOA and PFOS. In March of 2023, they issued a proposed draft national primary drinking water regulation for PFAS. They put it out for public comment. They received somewhere around 90,000 comments, and they finalized their drinking water rule in April of 2024. That final rule is applicable to community water systems and non-transient non-community water systems, but not transient non-community water systems. So PFOA and PFOS are set at a health goal of 0, but at a maximum contaminant level of 4. And then 2 other compounds at 10 parts per trillion, actually 3 others, sorry. And then they did a hazard index approach for the mixture of compounds, which is the first time that has been done in the United States. We are very concerned about this approach and not sure how this will play out. About 29% of our public water systems in Massachusetts are expected to be impacted by that EPA standard of 4 parts per trillion. EPA has acknowledged 3 treatment processes as best available technology. Those are granulated activated carbon, ion exchange resins, and high pressure membrane systems. In terms of our concerns, there's been so much focus of PFAS in drinking water, but we haven't sort of stopped the flow of PFAS into consumer products. This has created issues where different standards in Massachusetts than federal and even other states have caused customers to be confused. We have seen great variability in analytical results. So one system sent the exact same sample to 2 different labs, had an 8 part per trillion difference. When we're talking about a 4 part per trillion standard, that is really concerning. Our labs have been overwhelmed. We've had reporting delays. It typically takes about 6 weeks to get sample results back. The sample costs are high. We've had a lot of supply chain concerns. In Massachusetts, if your water was over 20 parts per trillion, you had to notice your customers that sensitive subpopulations should not drink that water. And Mass DEP required our public water systems to provide alternative water sources to those sensitive subpopulations, which is logistically challenging and very difficult. So I can certainly get into more during the Q&A, but those are some of the concerns that we've had. We also have a lot of high treatment costs, which you can see in this slide, and I know Natalie will be sharing that with you. We have other initiatives related to PFAS beyond drinking water, which are concerning. And then there have been legislative actions in various states, as well as legal actions to try and get at the manufacturers to help us deal with the remediation costs. With that, I will turn it back to Natalie. Thank you.
Thank you so much, Jennifer. It was really interesting to get the perspective there from the USA. And can I say, in terms of presentation skills, when I saw your slides, I was like, wow, 10 minutes is not a lengthy amount of time to describe the situation of a topic area in your country. I think Jennifer did an amazing job there. Next up, I would like to introduce a German perspective from Uwe. Just while Uwe's sharing his slides, I'm going to do a little bit of an intro to him. So Dr. Uwe Hübner is Senior Sales and Process Engineer at Xylem. He's responsible for treatment solutions in water reuse and advanced oxidation and has been since 2023. He's published more than 60 peer-reviewed journal articles in the field of advanced water treatment and reuse, particularly on the study and optimization of oxidative, biological, and sorbative processes and process combinations for the removal of emerging pollutants. Over to you, Uwe.
Thank you, Natalie. Good afternoon. Just to complement this, so before I joined Xylem, I was working at the Technical University of Munich, and this study actually are results that were taken in a project when I was working in research still. So from what we heard before, we're moving now back from drinking water to wastewater. It's more like environmental protection, what I'm discussing now, and how this is being addressed basically right now in the European Union. I want to go also very quickly through the regulatory framework. We heard already a lot this morning. There are basically 2 ways we can follow, or we do follow in the EU. And one is more, I would call it an emission-based approach, with the Water Framework Directive, where we define maximum values, environmental quality standards. They are called based on toxicological testing. And then we identify if we need to take action or not for the contaminants. The other approach is the Urban Wastewater Treatment Directive. And there has been a draft revision published recently. And this is more an emission-based approach. So it's just a comprehensive objective to reduce the load we discharge. Here we're talking about indicator chemicals, and those chemicals are not defined based on toxicity. They're just defined based on how they indicate the performance of the respective treatment process we have in place, and if we can use them because they're kind of always there and can always be detected. So that's more the basis for this indicator chemical approach. Right now, when we talk about advanced wastewater treatment in Europe, the second approach, this is mostly what we follow. So it's not only in the EU. Switzerland already has the regulation in place, and they're following this approach as well. Let's look at the status a little bit. So this is here showing Germany, Netherlands, and Switzerland as an example. In Europe, we have, that's very a rough estimate, we have about more than 170 systems treating chemicals in the wastewater before discharge. It's mostly activated carbon, powdered or granular, and ozone-based systems. And when we look at the approaches in Switzerland, also in the EU, the indicator chemicals are selected based on those processes. So that means they indicate the removal efficiency of those processes quite well, but they're not indicating if something is not removed. I think that's also very important to note for whenever you see some results from this advanced wastewater treatment. So basically, what we just heard on PFAS, those treatment processes are not designed specifically to remove PFAS. So they're not, that's not the way of sizing. I want to talk about a small case study we did in Bavaria. This is actually the first full-scale system, and it's kind of a R&D project, I would say. So what they do, they installed an ozonation system followed by biologically active filtration. And the filtration, they used two different systems, sand filter and an activated carbon filter, to compare those two processes. We had, after this was already commissioned, we got involved to do a monitoring study from TU Munich, and that was with the objective to first of all look at the performance, of course, then optimize the dosing or control strategy, also compare the efficiency, activated carbon and sand, and at the end to come up with recommendations for future operation. So there was a study for about 1 year. And I tried to go through those as good as possible. We, of course, generated a lot of data regarding the control strategy. The idea here, and in a lot of other projects, is to correlate the removal of UV absorbance. You can see this here for different chemicals. With the removal of the chemicals, you see some good correlation. And the advantage is the UV absorbance we can monitor online. So we would have then a direct measurement, and we would use those signals to kind of define what dose we need. To look at this in more detail, I mentioned already indicator chemicals. The concepts in the EU Urban Wastewater Treatment Directive use an average removal of a list of different indicators. So here in this case, we used 8 indicator chemicals we measured, and this is showing the average removal. Also here correlated with the UV absorbance. And this is from lab scale data using the water from that wastewater treatment plant. We also did this in full scale with different ozone dosages, and then based on this, you can say, okay, when we want to achieve 80% chemical removal, we need to operate the system at this delta UV. So this decrease of UV. We did 2 tests because we have a GSE afterwards. we went in one test a little bit lower so that we can have this combined, the 80%, and then we run a phase where we had the 35%. Don't want to go through this in too much detail here, but what you see is the operation regarding the performance here when you run with constant ozone dose and then compared to the different phases where we really focus on the removal of the UV absorbance. And there you can see that this is stabilizing the performance. And here you can see included in the same graph the results from full scale. You see there's still a scattering because that's not responding extremely perfect to changes. But you see we're getting in that range. Here's one point I want to mention. That was done at constant ozone dosage. And you see the correlation still works, but we have too low dosage. And that is just because in that particular moment, there was nitrite in the effluent or in the influent of the ozone system. And this nitrite is consuming the ozone and reducing the performance. Okay, based on this, we were looking into the treatment performance. Just want to let you know that this was done based on an outdated draft we had in Germany for a regulation, which did not come into force. And it used 9 indicator chemicals. So this 9 chemicals, and 6 of them need to be measured to have the average removal and to test, challenge, or validate the performance of the system. In the EU draft, we now have 12 indicators, which are defined in 2 different groups. So it's a little bit more advanced, I would say, but the concept is similar. So when we now look into 9 chemicals and we need to select 6 of them, you have here 84 different options to select 6 indicator chemicals out of them. Luckily, we were only able to measure 8 substances, so it's reduced already to 28 different combinations. But of course, you can imagine, depending on how you select the combination, you will also affect the removal you observe. And that's what we tried to look at in this project as well. So here you can see, I just walk you through the figure. You can see the average removal of chemicals in percentage. It's cumulated because that's the regulations say from the inlet of the wastewater treatment plant to the outlet. So it's including the activated sludge process before. And then we have ozone. And after ozone, we have the biofilter. In parallel to the biofilter is the activated carbon filter. And you see every of those lines is showing one combination. And interestingly, especially when you look here at ozone or ozone plus biofiltration, sand filtration, there is a difference of up to 20% between those different combinations. So you can really affect the treatment performance based on which combination you select. Just to highlight that this really covers a huge range. Those are 2 of those indicator chemicals, and we have some that are reacting much lower to ozone, and we have also highly ozone reactive chemicals that are extremely efficiently removed in this process. So that would even span a much wider range. And I also already mentioned there are chemicals that are not working very well in those processes. Here we measured the anti-epileptic drug primidone, just to highlight. So there the removal is much worse, and we would achieve, even with the GAC at the end, only up to 50%. Another example would be also the PFAS we just discussed before. So ozone is not removing PFAS. So if we have any additional chemicals that would cause problems because they are at too high concentrations to be discharged, then the treatment needs to not only be in line with the Urban Wastewater Treatment Directive, but we also need to look at the way Water Framework Directive, and this would be maybe then a change of the treatment process, which is required, or in adoption, maybe activated carbon to be replaced earlier. Okay, so I tried to wrap this up. One thing which is also important is this is really just the average removal from the different sampling campaigns. So when we look at one of them and see the statistics of individual sampling campaigns, we see there's even more variation. So then we have for this 50 to 80%, for this 70, 90%. So at the end, we can get from a removal of 50 to 85%, we can get any result in our individual sampling campaign, depending on what we're doing. Okay, I just very quickly want to highlight here one point. So how can we improve this? And I think there are two options. One is already done in the Urban Wastewater Treatment Directive and in Switzerland to really put them into two groups. So it's a group that is fast reacting, and it's a group this is a little bit less reactive, and we have to pick from both groups indicator chemicals. So that's reducing the range. And another idea is maybe we should look a little bit, focus a little bit more on surrogate parameters like the UV absorbance. For that, I want to finish and thank you for your attention and looking forward to the discussion at the end.
Thank you very much for your presentation there, Uwe. And you mentioned that there's major activities in the Netherlands, Switzerland and Germany in installations for removal of emerging contaminants. Maybe following the work that we're about to be kicking off with the School for Innovation, the United Kingdom will be up there on that list, the United Kingdom and Ireland, fingers crossed. So thank you very much for your presentation today. Next up, I'm just going to introduce him while he is sharing his slides. We have Daniel, who's going to be giving us the Belgian perspective. So we've got Daniel Model-Sperling, PhD researcher at the University of Antwerp. So he's doing research, him and his group, sorry, are doing research dedicated to the development and optimization of innovative bioprocesses for a sustainable water cycle in industry. And it sounds like he's doing a lot of collaborative work with a lot of different parties involved. And it was actually the International Water Association who got in contact with me about him presenting. So thanks very much, Daniel, and over to you.
Thank you very much. Can you hear me? Is this live?
Yep, can hear you perfectly fine, thank you.
Perfect, thank you. All right, everybody. Hello, nice to meet you. I'm Daniel. I'm from Belgium, and I'm here to present to you what we've been doing here about this topic. So to begin with, though, I'll tell you a little bit about ourselves. I'm part of a research group, BioWave, from the University of Antwerp. You can see us, most of us, in the picture up here to the top right at the last conference. Our mission statement is to develop, optimize, and apply sustainable biochemical technologies for water, wastewater, engineering, and reuse. Through my research group, I'm also part of Interreg, Clean Waterways through O3G, which is an international Dutch-Belgian collaboration funded by the EU, where different organizations, companies, universities, research groups, and the like collaborate to try to research and implement ozone and activated carbon technologies to try to combat organic micropollutants. Now, within our research group, most of us are focused on different specializations. I have a colleague who focuses on PFAS. For me, myself, I'm mostly busy with pharmaceutical residue products. Now, so I'll tell you a little story to get this scene a bit set. The Indian vulture crisis began in 1993 when 97% population collapse occurred across 3 different species of vultures in the India region. This has continued over the last several years, although steps have been taken. Alongside the tragic loss of life that occurred due to this, there was a rabies surge due to the loss of scavengers in the area, resulting in 47,000 extra human deaths and 31 billion euros worth of economic impact, converged roughly. The cause is eventually found to be a pharmaceutical product called diclofenac, which is a common anti-inflammatory drug used for humans and livestock. When we take it, we typically metabolize 50 to 60%, and then when we urinate it out, wastewater treatment processes handle 30 to 70% of it. Now, the rest of it ends up in the environment. I will say I've been slightly disingenuous with you all here in this context, because in this particular incident, the diclofenac entry method turned out to be livestock being eaten by the scavengers, and thus it was a fairly standard bioaccumulation effect. However, I do think this is a very good example case of how devastating any pharmaceutical product, the exact wrong one in the wrong environment can result in if even small amounts end up in an ecosystem. But so I'll get back to water specifically a bit more clearly, which is with the fish feminization phenomenon. This is something that's been observed worldwide. It's linked to several different substances, primarily estrogen, logically. But to put it simply, it's where a significant percentage of fish, there's more female fish and fewer male fish in rivers downstream from wastewater treatment plants, as well as increasing number of intersex fish. This is more of a concern rather than an active crisis, although I am aware that in at least one incident it did cause a population collapse. So this has probably been covered. What do treatment plants want to do when they remove this stuff? You've probably heard more about this already this morning, so I'll keep it simple. But for those of you who would like a clarification, the two treatment processes are typically ozone or activated carbon, where you bubble O3 gas through wastewater. The ozone absorbs into the water, binds to the organic products, and through its bonding breaks them into smaller and smaller fragments, potentially eventually turning them into CO2. Activated carbon, on the other hand, is simple filtration process where the organic substances can bite onto larger carbonous structures, such as you see here. You probably have one of these in your home. There's also a subvariation called biological activated carbon, which you've heard about in my predecessor slides. Basically, it's where a biofilm is growing on the surface of the activated carbon, and this can potentially contribute even more to removal, where it eats stuff off of the activated carbon as well as out of the water around it. Now, research has indicated that by combining ozone and activated carbon, you can have a bit of an interesting effect. While ozone doesn't necessarily fully remove micropollutants, just degrades them into smaller forms, it might end up many cases, ends up degrading them into products that are much more easy to break down for micropollutants and microorganisms. And thus, that's where my research focuses on. I personally try to study the application of microorganisms in this whole process and to try to optimize for their contribution, thus reducing the amount of ozone you need and potentially improving the activated carbon's lifespan. And to do so, I have this experimental setup I'm demonstrating here. This is a bit complicated, a little weird to show, but bear with me. So I work in collaboration with a local wastewater treatment plant called Aquafin Artslar, who contributes 60 liters of wastewater to me per week. I take half of it, I ozonate half, and I just simply aerate the other half. This is then taken where I filter it through different activated carbon filters to see the effect. In filters 1 and 4, I just have fresh activated carbon, where I'm simply seeing how the biofilm develops. In filters 2 and 5, I have completely used up activated carbon, where it doesn't really contribute anything anymore absorption-wise. However, they both have biofilms growing on them. And the idea is to see how the biofilm in the ozonated does versus the aerated one. And then finally, we have filters 3 and 6, where the water is simply being fed from the previous filter. The thing is, biofilms take quite a long time to develop on activated carbon, and we wanted to see if we could stimulate or amplify their effects by having them be inoculated by an active carbon filter that was already working. I also should mention I have filter 7 there, which is the same as the previous used activated carbons. However, in this case, it's been sterilized to act as a control. And on the right, you can see the experimental setup. That said, for all that prelude, this is still a bit of an ongoing process. So bear with me, so a lot of this is still under development or active process. For example, the micropollutants themselves. We're still in the process of developing an in-house quantification scheme. But in the meantime, we've been doing a little bit of initial measurements on how much we're removing with the two separate processes. So this is basically an early testament of how much we were removing from our indicator micropollutants. You can see our diclofenac friend there, where we're seeing fairly significant removal with the ozone process by itself, as well as the activated carbon when fresh is basically removing pretty much everything, although that does count down to like a 99% metric, so there's still a bit. Without the micropollutants immediately online, we're measuring organic carbon pass-through content, where we just measure the total organic carbon that passes through the filters. And here we see filters 2 and 5, the two used filters. The blue is showing how much is passing through the ozonated filter. The orange is the aerated, and the black is the sterilized filter. The sterilized filter. I should indicate that the vertical line is where we identified an issue of our ozonation equipment, so we had to adjust the concentration. But after it's fixed, we see that the sterilized is basically letting everything through. The aerated is letting a portion less through, and the ozonated is most successful. So at the very least, we are seeing what we're hoping to see here. As for the monitoring of a biofilm itself, in these instances, we're mostly planning to work with sequencing, where we're taking, again, long-term samples for. But for online monitoring, we're going with ozone ATP concentration on the surface of activated carbon, where the fresh activated filters are mostly growing at effectively the same rate and are showing similar traits and development processes. Whereas the ones that are used on the right are basically showing that, again, the ozonated filters are doing much better than the aerated filters in terms of liveliness. But that's basically where we are for now with our experiment. I thank you all for listening, and if you want to know more about either of these, my research group or the international project, feel free to scan these links. And thank you for listening.
Thank you very much for your presentation, Daniel. I thought it was really interesting that you saw the impacts on the species and the animal populations and then worked backwards to try and solve this issue. Obviously, in an ideal world, we'll be solving this issue before it impacts the ecosystem and humans. But I just thought that was a really interesting piece of root cause analysis, really, to help stop that in future. So thanks very much for your presentation. I'd please like to welcome back all of our presenters from that session to come join Thomas for a bit of a Q&A session. We've had lots of questions come through in the chat. Feel free to post further questions, but they've all been looked at so far. So don't worry if you've posted and we've not responded yet. Over to Thomas.
Thank you. Just to echo what Natalie was saying, some great presentations there. So really appreciate it. We're going to kick off with a question for Jennifer. So Andrew was wondering what the raw water source is in Massachusetts, and if in fact the raw water source is a big factor for PFAS in drinking water, in tap water.
So if I understand the question correctly, yes, I mean, PFAS is being found in the raw water. That is how it's coming into the public water system. And most of the detections in Massachusetts are turning up to be associated with the use of firefighting foams in that area or with industrial processes like metal plating manufacturing. So those are sort of where we've identified. I should say that, when it is found in drinking water above 20 parts per trillion, our Massachusetts DEP said that they would initiate a source investigation. We've had over 170 detections in Massachusetts, and they've only initiated about 49 of those source investigations. So we've got a great way to go in terms of figuring out where, the rest of the sources are. But AFFF seems to be a smoking gun for us.
Thank you, Jennifer. Uwe, there was a question here from a different Andrew, asking if you can clarify what you actually mean by removal in the process you walk through. Are the compounds like destroyed to nothing, or are they moved to somewhere else?
Yeah, generally that's based on the analytical methods. So in most cases, removal means the compound in its form is not there anymore. So we're measuring, for example, carbamazepine, and after the treatment, we're not seeing this anymore. It's absolutely correct. When we're doing ozonation, then it's not really removal, it's transformation. We know what we achieve with the transformation, of course. So in most cases, we also remove the specific activity, like for hormones or for antibiotics. It's very well known that the transformation also removes that activity. But of course, compounds are still there. And that's the question. If it needs to be dealt with, typically, we're currently not assuming this.
Okay, thank you. Next one for Jennifer here. How did the change in PFAS MCL impact your asset management or investment plans? Do the water companies in Massachusetts operate within a fixed investment cycle, and can you plan ahead to implement the treatment improvements needed?
It really has been problematic here. I mean, I had to breeze through the slide on the cost, but we're typically seeing, around $5 million per source for the installation of treatment, we have had our water systems have to increase their rates 30, 50% to cover those costs. So unfortunately, they typically have 20-year capital investment plans, but as new regulatory requirements come up, they're having to shift their spending to whatever the most pressing need is, and right now that is PFAS. We are also seeing that most of the funding for public water systems that comes through the federal government and through the state is being targeted towards PFAS. So that is not allowing our public water systems to do those sort of regular capital improvement projects that they need, like pipe replacement. So it's been very challenging.
Interesting. I have a follow-up question there, which, and correct me if I'm wrong here. This is just something that I've kind of heard through the grapevine and having these conversations, that there are some water companies in the US that are taking the fines instead of actually addressing the kind of regulatory environment. Is that incorrect, what I have heard, or what's the story there?
I know that question was asked during the regulatory process. In Massachusetts, that is not the case. There have not been fines. People are on administrative, consent orders or notices of non-compliance to come into compliance with the standard, and it is expected that they do so.
Perfect. Thank you. Another one for Uwe. How do you delta UV control in practice, since the residence time is minimum 20 minutes? Do you adapt the dose every 20 minutes or more or less often? What if your flow rate is higher and thus your residence time is even more than 20 minutes? Do you then adapt your control time interval? Hopefully that is clear.
Yeah, it's clear. It's a really good question, and there has been a lot of research on it. So especially since it's also combined with the discussion of fouling of the sensors, and we know that biodegradability increases during ozonation. Daniel also showed that, so that the effluent sensors are fouling even more. So there has been even an idea to look at measuring after the biofilter. But then we see exactly that point happening even more, that the retention time is too long to respond. We not necessarily need to wait always 20 minutes, but we need to adjust that according to the contact time in the reactor. So that means we're waiting always for the effluent signal 20 minutes, although we can of course measure continuously. This is especially when the water quality is changing rapidly. This can be a challenge, and you've seen some scattering in the data also there. And this is probably due to this effect that in those times, especially when we have a stormwater event where rapid changes are occurring, we do have still some problems with that. So we're working on other approaches to be more stable in that, but overall it works already quite much better than other concepts. That's the conclusion I would take from the study.
Thank you. Daniel, one quick question for me. Has the vulture population in India, has it recovered?
From what I was reading about that, to some extent, yes, although it's still in dangerous levels, apparently. They implemented legislation to crack down on the pharmaceutical medicines causing the issue. However, apparently there's still some traces being found that are at dangerous levels, but they are working on it, from what I saw.
And I've got a question here in the chat for Andrew, which Anna, maybe you can have a go at as well, which is, we've heard a lot about combined ozone charcoal biofilm approaches for wastewater. And given the challenges of the treated wastewater matrix, do you think it's affordable long term to implement these kinds of solutions for the customer?
Okay. Sorry.
Go
ahead.
You want to say something to it? I can also respond.
No. Go ahead. You're first. You're a bit more closer to that area than I am.
So in general, this combination is needed. So I mentioned before we need a biological treatment after ozonation because we generate some products that are easy biodegradable, that are aldehyde compounds and so on. And they would be removed anyway or reacting. And we don't want this in wastewater to occur in the rivers. We also don't want this in drinking water to occur in the distribution system. So we need a biological treatment process. And the question now is, that's raised by Daniel, is are we using sand or are we using something more active? And the biologically active carbon is a solution that would speed up the growth of microorganisms there, and would also give some additional removal for absorption. And at the end, we would not need to frequently replace the carbon. So that's why it seems to be a quite affordable and promising solution.
From my own 2 cents, if I may also add a little bit, I've seen a bit of talk about research on this topic. They're both independently can be, you're right, a little bit expensive or energy costly in order to implement, especially but from what I've also seen, a lot of companies and a lot of research groups are actively working on trying to optimize both of these processes. I've seen research into activated carbon biofilms that have dramatically increased the lifespan of activated carbon. And by using that, you need even less ozone, thus trying to make the optimization better. So while I will say that if you do look at the raw numbers now as they are, it might be a little bit intimidating, there are pretty dramatic strides being made on this front, at least as far as I've seen.
Okay, thank you so much to both of you. As much as I want to keep this conversation going because it's super interesting, I think we'll have to wrap up and move on to the next section. So just want to say thank you to our 3 speakers. Please stick around if you can. We have an interesting panel discussion next, and great to hear your challenges, questions, and inputs and builds to that. But yeah, thank you so much to our speakers, and sorry for anyone that we haven't managed to get to the questions of. As Natalie said at the start, we do have a slightly tight schedule for us this afternoon. But thank you, Jennifer, Uwe, and Daniel for your input here. Really appreciate it.
Pleasure.
Just to echo again what Thomas just said, thank you again for our speakers. I think it's so invaluable to get that international perspective, those lessons learned from other countries who have maybe been working in this area for a little while now. I feel like we have a lot to learn from some of the work that they've been doing, and especially in those countries where maybe the regulations are a little bit different to what they're looking like in the UK and Ireland right now. So thank you very much for that. I think it was really, really insightful to get that. So next up, we have the meat, you can almost say, of the event today, both of the morning session and the afternoon session. This for me is the most exciting part of the event. This is the art of the possible. So we've looked at some of the context setting in the morning session. What is this topic area, bringing everyone up to speed? We've looked at some projects that have gone on sort of in the past and are currently happening right now. Now it's time to look at what could the future be for the UK and Ireland in the emerging contaminant space. What should that call for innovation be looking like? What research questions, what problem statements should be going forwards that the global innovation supply chain academics can be applying for? To do that, we have a series of amazing panel presenters today. We have speakers from UCWIR, the UK Water Industry Research. We have people from the UK Centre for Ecology and Hydrology. We've got Severn Trent. We've got the Water Research Centre, WRC. And we have yourselves, everyone who is present in the room. We've just had a reminder put in the chat for you to go through as we're going through the panel discussion and answer some of those questions that the panel are asking. They're going to be inspiring you, so you can think about what you would like to say back to them or what your opinion should be in that space. So I'm going to hand it over to Thomas, and if all of our panel presenters could please turn their video on in preparation for this session. Thanks very much. Over to Thomas.
Welcome, folks. Me again. I just to echo some of the stuff that Natalie's been saying, got the pleasure this afternoon of hosting this panel, which we're kind of loosely calling the art of the possible. So far today, we have spent a lot of time looking backwards, right? Understanding emerging contaminants by looking to the context, looking to what it means from a business and a regulatory point of view, looking, as Natalie was saying, looking to some projects that have been run internationally. Now, I'm joined by this great group of experts who will introduce themselves in just a moment to flip our perspective a little bit and to look to the future. So helping us to uncover the types of things that we need to do to understand, to measure, to take action. You know, where should we focus our challenge to create value for water companies, customers, and the environment? As a brief reminder, we've got just over an hour, about an hour for this section. So we're looking for about half an hour or so of panel discussion. Then we'll open up for about the same for audience participation in Q&A. And as Natalie said, we've posted the link to the kind of questions in the chat as well. So please do input in there, because we are asking essentially the same questions to you as we will be to the panel. So maybe let's kick off with a round of introductions. I'm going to ask each of the panel members to give, the audience a 30-second or so just introduction to yourselves and your backgrounds. Jenny, do you want to start with you?
Sure, thanks, Thomas. I'm Jenny Hughes. For those of you who weren't around this morning, I was Strategic Programme Manager, looking after wastewater and sewerage and substances of emerging concern. Previously, I was at Thames Water, where I looked after the chemical investigations programme for about 10 years. I'm not a chemist, I'm an environmental scientist, but a bit of an overview on all things chemical and researchy. Thanks, Tom. Over to the next one.
Thank you. Andrew.
Yes, hello. I'm Andrew Johnson from the UK Centre for Ecology and Hydrology, which is a research institute in Oxfordshire, where I'm based. I've spent almost 30 years now looking at the impact of chemicals on wildlife, primarily in rivers. So I've been around the block quite a few times. There are still more questions than answers.
Thanks, Andrew. Ehi.
Good afternoon, everyone. Thanks for inviting me. My name's Ehi Taylor. I work as a principal toxicologist at the Water Research Centre. So we're a small group of toxicologists, hopefully termed the National Centre for Environmental Toxicology. So we support primarily the water industry, but also the clients from the environmental sector as well, looking at chemical fate and chemical environmental fate and chemical risk assessments as well. I specialise in chemical risk assessment, and so we're interested in all chemicals, environment, chemicals of emerging concern. I'm concerned as well. So it's quite broad our interest. So looking forward to this discussion.
Thank you so much. And I can't see you on my screen, but Gemma, are you still with us in the room?
Yeah, I'm here. Can you hear me?
Perfect. I can hear you perfectly fine. Yes.
Yeah.
Hi.
Hi. Yeah, so I'm Gemma Hill. I work as a senior innovation director at Severn Trent, and I am leading on our innovation emerging needs program of work. So that program contains projects on PFAS, antibiotic resistance, and microplastics. My background is actually microbiology, and specifically around antibiotic resistance.
Amazing. Yeah, I mean, I think everyone can tell that everyone on the panel here is a technical expert, minus me. I am not. So panel, please forgive me if I prod a little bit for additional clarification, or ask you to simplify explanations for me, or maybe for people in the audience who may be a little bit newer to this topic. So I'm going to kick us off with quite a broad one and get the kind of grey matter working, so to speak. What are the big questions in emerging contaminants? Andrew, we'll start with you.
I suppose I have a slightly different perspective in that I've seen emerging contaminants, as you might call them, come and go. And there's a sort of timeline that goes from alarm to panic to a lot of research, often finding less impacts than we thought, to declining interest, to panic over the new compound that is found tomorrow. and so it goes on. I think when you're thinking about from your perspective, on the one hand, sometimes you get focuses on treatment methods that might be unique to the contaminant of concern. And examples might be very specific, almost immune system approaches where you just take out a single chemical from a wastewater stream. Now, as that interest waxes and wanes, you're probably better looking at broader technologies that can remove a whole range of micro organic contaminants, such as we've heard today. But the whole issue doesn't exist in a vacuum. There are other pressures that we know are on the sector, particularly about energy consumption. And so one of the things that you often don't hear that much about is the extent to which an efficacious method might actually require a huge amount of energy and hence more CO2 going into the atmosphere. And you often don't hear about how we balance that. More biological focused methods have the attraction of hopefully using less energy, but they may be more unreliable and not as efficacious. So we're sort of struggling between really high-tech, high-energy methods and more biological ones, which maybe use less energy and are less efficacious, against a background of uncertainty with, I suppose, regulation and what the next fear might be. So it's not an easy position to be in for you and your water industry customers to view this future.
Gemma, does that ring true to your experience and kind of your on the ground, what you guys are dealing with at Severn Trent?
Yeah, it definitely does. I would agree that when we have projects, they quite often will focus on one need at a time. And I would echo that we need to be looking at broader technologies that do tackle multiple problems. And it definitely, I think, sometimes there are missed opportunities to evaluate whether technologies are effective at removing multiple contaminants in one go. And with that, I think there's definitely a question around, it was mentioned this morning about like cocktails and impact of mixtures, and I think there's a really important question about that. And I think that's something we don't really look into that much at the minute currently. And I think we should be probably looking at that a little bit more, looking at like overall toxicity measurements and looking a little bit more holistically at our water quality, both on potable water and our river water, and sort of making sure that, yeah, we do understand from a broader level what's going on, and then looking at those broader treatment options. And when we are looking at new approaches, I agree that we need to be evaluating not just are they effective, but how efficiently they're doing so, how energy intensive they are, and what then is the impact of that, and if there's any unintended impacts of it, not just maybe excessive energy usage, but also like byproduct formation. So making sure that we're really monitoring everything and getting a really good understanding of the technologies that are out there and how practical they're going to be for us to actually use.
Thank you. So I guess Ehi, that kind of takes us, I guess, to the next question that we've been kind of contending with, which internally at Spring we've been thinking about the emerging contaminant space as in kind of several different blocks or kind of pillars. So identifying the contaminants, understanding their sources, your lab methods and instrumentation, and then actual treatment processes to sort of remove or mitigate them. First of all, in your opinion, is this the correct mental model for us to be thinking about the emerging contaminant space in? And if so, where do we want to play? Like, where's the best space to intervene that ensure we're creating value?
I think that's a really difficult question. I think obviously the only way to actually address the issue is to actually understand whether there's a problem in the first place, and to do that you need to have effective monitoring, and to do that you also need to understand, well, what's the state of the problem within the different well, I guess within the breadth of the water cycle, and the different stages or the different locations as well. I think it's really important to monitor, but again, understanding the problem is about, so for example, if you take PFAS as an example, it's really important to undergo testing in, where you have, wastewater, and to understand, well, actually, where are the sources, where are the most problematic areas. At the moment, there isn't a drive to do that. I'd say that, yes, there's a requirement for water companies to monitor, to meet the regulatory requirements, but are we actually monitoring in the right areas? And that's, it's not a question I can answer, but certainly from a toxicology perspective, in some ways you have to kind of take a pragmatic approach to the problem. And so it's been mentioned a couple of times. It was interesting to hear one of the speakers this afternoon talk about the fact that the US EPA, it's the first time they've used the hazard index approach. And although I did sense a bit of ambivalence for the use of the hazard index approach for that, but one would argue that actually, when you have a compound like PFAS where there's just thousands, it's impossible to regulate such a huge group of compounds. And so on one hand, you have the EU approach of, well, let's regulate and let's try and move to banning this whole group of compounds. But from a toxicology perspective, the data just isn't there. And at the moment, we don't know enough about all these thousands of chemicals. And so the only approach, and Jem rightly said, we do have to look at the effects of the group, the cocktail effect, for want of a better word, the term that's used a lot. You do have to start moving towards managing groups of compounds and actually considering what the impact of those groups of compounds are. So it's a really difficult question, but I think there is a need to have a holistic view of the process and the whole process as well.
Interesting. I think, Andrew, that sort of feeds back into, or at least in my head, feeds back into what you were saying before about this kind of the next contaminant coming up being the hot topic, and then sort of fading away as the next one becomes the hot topic. What's your opinion on what he just shared?
It's been a fear of mine for a long time that our responses to chemicals are not proportional to the risk. And as I say, there's this sort of kind of naive, it's a human aspect, I suppose, that the new compound we've just discovered must be far more dangerous than anything we've looked at in the past. And we sort of lurch towards this new fashion. And actually, if you try to look at a balanced risk assessment across all the different chemicals present that are discharged, many of the new ones would fall a long way down the relative risk ranking. In other words, some of the older, more boring chemicals are the ones that still present the greatest risk to wildlife and rivers. So I do fear that we do react. We tend to be far more reactive. And I think the thing also, I suppose the water industry must itself just be a reactive participant itself. But this is the question about regulation. But most of the direction of the way we operate is top down. In other words, we sort of presume something is risky, maybe from experiments we've done in the lab, and we very rarely consider things as bottom up. What I mean by that is we very rarely review the health of wildlife in rivers downstream of our wastewater treatment plants. So, well, much of England, of course, has quite a high exposure to wastewater because we're a small, densely populated island. But in fact, when we do that, the wildlife can often found to be surprisingly doing well and breeding successfully. And an example of that was the endocrine disruption story we heard about a little earlier, that was a big issue in my career, where we thought that the effects we were seeing on individual fish showing signs of endocrine disruption was likely to be catastrophic, but in fact it found that fish, even with effects of endocrine disruption from steroids, were breeding successfully, and so the populations weren't actually at risk. And ultimately, the Environment Agency itself started to lose, I suppose, some enthusiasm for really charging on with endocrine disruptors because the population seemed to be quite robust. So as the data emerges, we might find that the compound that we're terrified over today is not such a problem after all. But I think that the water industry, I think, is too much on the back foot, reacting to scares, and I don't think it does enough on the front foot of looking itself on the state of wildlife in rivers, and it might be quite pleasantly surprised by the what it finds.
So if you were just to jump around a little bit, if you were, are you saying that you think the focus of our challenge could look more at the impacts of these chemicals or substances on ecosystems or humans rather than on their monitoring or analysis or treatment?
Well, kind of, yes. I mean, we've heard a bit about words like mixtures and cocktails, and this is the sort of thing that tends to, if you like, increase our anxiety when we think of the great range of chemicals that wildlife or indeed humans are exposed to. But rather than sort of being in the dark about that, you find that if you actually look at wildlife and all the challenges that they face, you might find that actually the biodiversity and the richness is doing quite well and it's improving. Maybe the abundance can vary, but it could be that wildlife are far more resilient than we think because they're also compensating factors. So basing all our judgments and fears just on laboratory ecotox data, you can tend to perhaps exaggerate the risks that you're facing with a chemical. And I think it's important that we review this carefully before reaching out to incredibly expensive, high energy solutions to something that may not be quite such a problem as we thought. Now, we don't think like that with drinking water because, you know, if one baby gets sick in 10 million, that's a big issue. But it's not an issue for animals in water, in rivers.
Does anyone on the panel have a contradictory opinion, want to challenge anything that Andrew's saying or echo it at all?
I can't say I agree entirely with you, Andrew. I think one of the problems is it might be that if you take a snapshot and you find that the diversity is not unaffected, it's fine maybe at that point of time. But I dare say you'd have to have a long-term monitoring program to actually see whether or not that snapshot is reflective of, or at least have some kind of comparison with what's happened previously and how long it's been happening. I'd be reluctant to say all is fine without without the supporting data to actually confirm that.
I think we also have to consider that emerging contaminants aren't the only thing that might be impacting the environment. Obviously we see climate change whichever way, more water, less water, warmer water, colder water. We can't necessarily differentiate without perhaps dissecting things and seeing how they've reacted to increased concentrations maybe.
Gemma, do you have a view on this, or?
I think we could do more for monitoring sort of the ecosystems. We could monitor the rivers better, and I do think there's definitely something in that. But I think ultimately we still need to be monitoring all these contaminants of concern because they're a concern for a reason, and if later on they get disproved, if it says, okay, these are not toxic, this is fine, then I think we're always going to have to err on the side of caution, right? And I think we have a responsibility as the water industry for potable water and a waste side that we're going to have to be cautious. We can't assume anything. And so if there is a concern out there, I think we do have to address it. But I do think, we could be doing more to monitor our water quality in our rivers for sure. And I think there's definitely more talk about eDNA monitoring and community analysis through that. And that could be a way in which we start to build up some profiles on how actually our river quality is being impacted and whether it actually is being impacted. So I kind of sit in the middle, I guess, more towards, I think we just need more data on everything. I don't think we can dismiss anything, and yeah, but we can definitely do more in sort of all areas. But obviously we're limited as well. I say we can do more. Obviously it's not actually practical to do more. There is definitely a want to do more though.
Okay, interesting. And a moment ago, we were speaking about, the sort of relatively reactionary historical nature of the water sector. And I mean, by the very definition, these, contaminants or micropollutants are often unregulated. So, Jenny, maybe a slightly tough one for you, but where do you think or for not just for you, but in general, where do we think that the regulatory environment might be going over the next sort of 5 years or AMP period? And therefore, like, how do we ensure with our challenge that we're kind of skating to where the puck is going rather than being reactionary ourselves?
Yeah, I know that Megan mentioned this morning, particularly on PFAS from the DWI, they've had, I think it was 5 letters across about 9 months about different sort of standards and varying that. And I think for drinking water, we're very quick to react because the human health impact is always at the forefront. Water companies have to provide wholesome water to their customers. Full stop. That's it. Doesn't matter how you get it. You have to achieve that. I think on wastewater though, the story's a bit different, and I think within the next 5 years we're probably not going to see much. We might see some start of some ideas around it, but I think at the moment, unfortunately, the biggest challenge for the water sector is on the CSOs and the discharges. In that respect, people are more worried perhaps about sort of the general sewage in the environment. They're not worried about the parts per trillion of X in the water and whether that's a problem. But that's not to say that we shouldn't be thinking about that, because it is part of the bigger problem. People want to be able to get in the river to swim safely. Yes, we need to sort out some of the other problems, but it comes back to we can't treat everything in isolation. We can't just go, right, this problem, let's do 4 things that fix this. Right, what's next? Let's have a look at that one. I think we need to be a bit smarter and perhaps not just always wait for regulation. While it is going to, take some time to come together, I don't think we can wait for the push. We should be pulling rather than pushing some of the time. So like I said, I don't think we're going to see much change, but I think we should try and work with the regulators as well to inform them about the sort of achievability. And as we've seen in the US, the concentrations that are being required, analytically impossible. Are we going to end up in a similar situation where we're looking for quadrillions of something and we can't monitor that, so we can't find a measure to get us to that?
Interesting. So building on that, Ehi, do you, from like a spring point of view, do you think that we should be addressing a specific chemical or substance or family of substances? So is it PFAS we want to be looking at, microplastics as a general category, pharmaceuticals, something more niche like we heard about the sheep dip from the Welsh regulator this morning? Like, where is the highest leverage point for us to be thinking about?
I think there's so many that you could choose from. I'd say it goes back to what's quite topical. I think it's clear that the regulators are struggling to deal with the PFAS problem. It's not just a UK problem, it's a global struggle. There's not enough data, and so which is why the regulators aren't able to keep up with it. And why it's also taken this long for them to actually come up with a value. And in some ways they're waiting for, other expert committees to actually have a viewpoint on it before they're able to actually commit to any one number. We've also seen that it's, just, I think in some ways the US EPA have been, the US as in whole have been, they've been at the forefront of actually setting standards, and everyone's been looking at that. But if you look across the US, it varies so much depending on what the driver is and what the different state drivers are. I'd say you could choose PFAS. It's not it's one of those problems that's not going to go away. I think the problem is that the legacy of PFAS is only becoming more evident, and that's why it's probably likely to stay for a while. One of the difficulties is there as well is the fact that it's so difficult to analyze, and so not only is it difficult from a data perspective, it's also difficult from an analytical perspective in that, yes, there's a requirement for water companies to detect it, but it's so hard. It's unless you're actually using the right techniques, which also need to be validated, there just isn't uniformity as well. And so I'd say microplastics as well. They've had a lot of there's a lot of publicity on microplastics, but I wouldn't necessarily say that it's in terms of the risk profile. I wouldn't say it's necessarily high. The evidence just doesn't support it at the moment to say that the risk to humans for example, from oral exposures is high. The evidence just doesn't support that at the moment. But I'd say it's one that, if you look at microplastic, it's one that the water companies probably need to keep an eye on. More from the environmental perspective at the moment, I'd say that's the driver. So it really depends on what you're looking at. But again, it's a difficult one because you can't look at each chemical group in isolation, but equally each one has their own mammoth requirements. PFAS on its own, it's whether or not whatever analytical techniques are being derived for PFAS are also applicable. You would hope that they are applicable, especially when you're looking at limits of detection at such low levels. And you would hope that whatever is being developed for PFAS would also be applicable to other emerging compounds of concern. I'd say when you're investing so much in analytical techniques and testing and treatment options, I'd agree that you should look at a variety of compounds, whether it's microplastics, and it's in a similar way where you could say, well, GAC is quite effective for removing a whole breadth of compounds and contaminants. I think a similar approach, the water companies and just research and development efforts should actually be looking at those sorts of things rather than just saying, okay, we're only looking at PFAS and how effective it is at removing PFAS. I think the drive really should be on PFAS, but also other contaminants as well, other emerging contaminants, because let's face it, they are going to still be there. It just depends on actually, well, at what point does the for example, the toxicology data support the fact that actually it's now, with a lot of these chemicals, it becomes an emerging concern when the data suggests that actually it's now of concern. There's enough data to suggest that it's now of concern to humans or is now of concern to the environment because we now know more about it. Yeah.
Yeah, makes sense. Thank you. Andrew, we've spoken a little bit about regulators. Are there any other sort of key players or stakeholders that, innovators, people who are building solutions in this space should be aware of, consider, or consult outside of the sort of water companies and regulators?
I think it's a difficult game to play because we sort of mentioned the general public before, and there are actually quite a wide range of chemicals we could be worried about, and for some reason one thing will kick off and capture the imagination. I remember a Japanese academic colleague about 15 years ago, and he used to go around everywhere around the world, and he would test tap water in the hotels for PFAS, and he'd nearly always find it, and he would measure it and report it, but he couldn't get a soul to take any interest in it whatsoever. Everyone thought it was a very boring subject. He would be much better employed looking at maybe endocrine disruptors. Now, this makes it difficult job for everyone here to look towards the future because it can be driven by that huge upsurge in unpredictability in public interest. I was just thinking more generally about the field of chemicals in the environment that we're sort of thinking about this afternoon, and one is, we'll be back here again. If you think about it, society badly needs chemicals that are unreactive, and persistent. You can think of 101 uses around the home, the hospital, your clothing. We like things to last, and we like things to be non-reactive. So you can put any sort of liquid in them and drink it, and it's wonderful. And this is why we love plastic so much. And the PFAS compounds and things before them were incredibly useful. So as we move towards banning them, undoubtedly we'll be replacing them with something else because we need those properties. Now, the great news about things that are persistent and non-reactive is they're really, in a way, quite economically very valuable and efficient. The bad news is, as we all know, is that they hang around in the environment forever when we discharge them, and they may have very slow, subtle effects on animals very high up the food chain. So even as we perhaps move to banning things today, society will want a replacement tomorrow. And if you say, yeah, I've got a replacement, but it's much more biodegradable and will disappear quickly, boy, sounds good, but then the properties may not be the ones you want. Similarly, we're always going to need intensive insecticides that are highly, highly toxic. And we love them. They're efficient. They do what we need. But then, lo and behold, what do the ecotox tests say? And we're then terrified of them. And then we thought, well, we can't afford to grow crops without them. So society's needs for chemicals means that we'll be coming back to this sort of emerging contaminants seminar another 5 or 10 years. It'll keep happening.
I suppose then, Andrew, do we need to look to the manufacturers to make a change, because the people will only use what they're given to use, won't they?
Well, you could do it that way, or you could say we can't escape the position we're in morally, that whatever I think of the relative merits of the toxicities of the chemicals involved, perhaps there's a moral argument that we shouldn't be discharging them into the environment. And therefore, there's a moral argument to push on with the treatment technologies, the tertiary treatment technologies. And perhaps we have to reconcile ourselves to that. And therefore, the pressure from the technology side on is, can you do what you're doing now at a fraction of the cost and the fraction of the energy consumption?
I think so. Just to jump on that point, Jennifer just made, there is a whole new area of chemistry that green chemistry, looking exactly at that. Obviously, it's it's decades in the making, but the whole idea is we now know so much more about problematic chemicals, or the chemical properties of certain chemicals that are likely to be hazardous, and the whole area of green chemistry is looking at to try and avoid some of those characteristics of compounds, to try and design safer and more and equally effective chemicals. But obviously it's not it's a long-term solution, and also there needs to be an investment and a willingness from companies for it to be, well, it has to be economically viable. Let's face it, they're out to make money, and so what's going to be, it's I think it's good that the public are informed about it. It becomes a case of how well do we manage the information, and how well do we communicate the risks, and manage the perceptions of what the public might seem or deem to be a problematic chemical, and actually informing them about whether actually their perception matches the reality of whether it is a concern or not. That's a whole other story as well.
Thank you, Eddie. So I'm going to move on to our kind of final question, which I'll get everyone on the panel to answer. But first, I just want to echo what Natalie is saying in the chat. Please do give us your feedback, your thoughts, your opinions on the questions that we're asking here. We want the wider audience's view, as well as these four expert voices. So Gemma, I'm going to start with you. If you were in our probably unenviable position of designing a call for innovation, looking for specific implementable innovation for water companies to trial, progress, adopt as a collaborative group, what would your research question be? What would your challenge statement look like?
I mean, there's definitely a few. If you just, I'm not sure if you just want one. I mean, I guess one of the main things there's water industry interested in is, so how can we optimize our existing treatment without overloading it? What modifications could we make? And then if there isn't anything there, what new technologies do we need to be looking at to help solve the problem, or not all problems, but to help solve some of the problems that of emerging contaminants. And then like with that, as we've discussed, to evaluate fully what are the potential unintended consequences of using such technologies, to evaluate properly like any byproducts and air emissions, and to make sure that whatever is suggested is scalable so that it's actually usable for us, and that it will be able to meet future regulations as things are changing. So something that, yeah, can be evolved. Yeah, that's probably one of the broader ones. There's quite a few, but because I think the other thing there, and definitely one of the other areas that I'm definitely interested in, is like understanding the environmental factors that are involved in persistence of contaminants in the environment. So any sort of thing that helps us sort of monitoring, like source tracking, monitoring like breakdown products, and maybe helping us to predict what's actually coming to us, and more on the water side. Anything that helps with that, that helps us then prepare what technologies we need in the future. I think that's what area definitely needs more work.
Thank you. And yeah, just to reiterate something I think I've said a couple of times today, we're not looking for a single shiny, beautiful challenge statement at the end of this. We appreciate that we're starting at quite a broad set of the funnel, and we're trying to refine it slightly during this conversation. So yeah, I appreciate the kind of multi-pronged answer there, Gemma. Jenny, same question to you. What would your challenge statement be? What would your research question be? And if you were doing the same thing that we're trying to do here?
So I started to think about this as so we have our big questions, and I started to think of it as one of those because it is such a big question. So for me, I've got how do we, being the water industry, with the support of regulators and perhaps technology providers or anyone else in the space who is able to, address emerging substances within drinking water or wastewater or both. There's a lot of caveats and options within my statement, sorry. How do we do this in a sustainable and adaptive way to be able to meet the future challenges too? So this is not just addressing the here and now. This is when we find something else in 5, 10, 15 years time that we don't just need to add. I mean, we're already looking at quaternary, you know, we don't need to add on something else after quaternary to get us to that treatment stage. So it's sort of, it's the fixing the problem now, but also planning for the future. How do we prepare ourselves for that?
Perfect.
And then on top of that, as a part B, what do we do once we've taken it out? Because that's something we often forget about. You know, we've got this brine, or we've got this product that's full of all these emerging contaminants. What on earth do we do with it now?
Yeah, we had, I think someone said earlier, is it problem solved or problem moved? So I like that little addition. Andrew, same question to yourself.
Yeah, before I attempt to answer, Thomas, there's quite a lot of interesting chat on, some of it directed at the panel that actually is.
Yeah, we'll move on to audience Q&A directly after this. This is the last question.
Okay. Well, I think thinking to the future, I think there are two sides. One is, I think from the environment point of view, we ought to keep our feet on the ground and look for the evidence of harm on the ground in the field before we have, you know, perennial sleepless nights over it. And I think if I was a ratepayer, I want to know, if I'm going to have my rates go up 50, 100 quid a year, I want to know what the benefits are in the river that are happening, that are measurable. If there isn't a measurable benefit, or people just aren't even interested in my question, I'd be disappointed in that. But I do think that's part of better monitoring that we've discussed a little bit before. I think the likelihood is that there'll be pressures from different directions, that perhaps if not strong today, probably stronger tomorrow, to advance wastewater treatment to remove more substances and tomorrow's substances. So broad removal technologies, such as some of we've heard today, I think that will remain. And I think there is a technology question. And maybe I've seen hundreds of grant proposals on new technologies to improve wastewater treatment, but usually they sort of fall on the kind of naivety of problems over biofouling or energy costs. But maybe there are more that will come down the track, and we should keep a close eye on that, because it probably will have to come in.
Okay, thank you. And Ehi, last but not least, same question to yourself before we move to some of the audience questions.
I think it would be really important to try and look at this holistically. And in order to do that, like you say, you don't want to, solve one problem, choose one contaminant, and then, a year later, 2 years later, you're then having to look at another one. I think the problem is looking at each of these chemicals in isolation. But equally, I think it would be nice for water companies or the industry as a whole to try and take a more systematic approach. So I would be interested in, in supporting a project. If I have the money and I'd say I'd like to support a project, I'd like to develop a project where it looked to develop a tool that approached it in a systematically evaluated all the different drivers, the primary drivers. So if public health is our concern, what are the main primary drivers that will influence our decision, to choose, one or a handful of chemicals, so that's the approach that we take. Within my role, I'm looking at chemical risk assessment, and we have maybe 700 odd chemicals that we kind of systematically review. And it becomes difficult to choose just one, or if we have, say, like 90 within a year that we need to kind of review and update and say, is the information consistent? We've developed, a systematic approach to looking at that, but we have a number of indicative factors. So, is it easy to assess the risks? Is it a chemical of concern? Is it on the radar of regulatory bodies? Is it easy to treat? Is it, those would be the sort of things that I would look at. Develop a tool, but that's systematically evaluated. So you're having a kind of risk approach to kind of ranking the different chemicals. But it would mean that you're not then looking at just one, you're looking at several at a time. Mm-hmm. And it's then easy for you to then see, okay, well, this is up and this is down. It's not just driven by the public perception, it's driven by consideration of the impact to the environment, the toxicity, the availability of the data, and also fundamentally the ability to group certain groups of compounds rather than just looking at one or two. And a primary example would be PFAS. There's the ability not just to look at a single PFAS. You're not just looking at PFOS or PFAS. You're looking at a whole group of compounds. And so I think it needs to be that sort of approach, because it's difficult to just choose one or two of these chemicals of environmental concern or emerging concern even.
So almost like a red, amber, green risk assessment for variety of chemicals. I'd be interested to ask the audience if something like this already exists for these contaminants. Is anyone aware of anything like that? Please you can post it in the chat if we know or not. It sounds very interesting. While people are doing that, I'm going to move on to some of the audience questions. So Gemma, first one up for you. So Severn Trent have the Ofwat breakthrough project on PFAS removal, and the question is, sorry, I just lost the screen. What's the scope for ion exchange based pilots under this?
So the Ofwat bid that we won was for PFAS destruction. So it's a follow-on project from the existing project with DWI and Cranfield, which is investigating removal. And as part of that, they were looking at ion exchange as one of the removal technologies, and that was against ion exchange. There was GAC and nanofiltration, looked at a load of different removal technologies. I think that's coming to the end, because we're going to use that and the outputs from that to then feed into our destruction project. So yeah, we'll take the lessons learned from that. We'll look at the best technologies, and the idea is basically to come up with more of a complete treatment train, so that to basically destroy the PFAS that's in waste streams generated by processes such as ion exchange, because the ion exchange is an effective way to move PFAS, more effective than GAC, and it's going to be better for when we have short chain PFAS. But what it's going to do is create a really concentrated waste that we're then going to want to destroy, because we could send it to the wastewater treatment works, but we will be creating more problems for that. And then is this going to get cycled back into the environment? So what we really want to do is break that cycle. So the off-what bid is, yes, a continuation of that project. It will look at ion exchange, and it will be in combination with various different destruction technologies. And going back to what you said at the start, that we want to evaluate them sort of comprehensively, to look at energy consumption, then like total costs of use, like how long they last, and then how effective they are, and byproduct formation, and to do it more like as a comprehensive piece of work with Cranfield University. It was related to pilot plants, wasn't it? Because the Cranfield work is going to be lab scale to begin with, and then the idea is that we take the most promising treatment trains and then we pilot them. So it might feature as part of a pilot treatment train.
Great, thank you so much. Jenny, I'm going to come to you now. So do you think that the water industry can actually look at treatment options for this ever-changing landscape of chemicals and actually be as holistic as Andrew was highlighting earlier without the support of regulation?
Simple answer, probably no. Ultimately, we often see that regulation drives funding in the water industry, that despite what people think, the water industry don't have any money to do a lot of these things until they're told to. But I think we can perhaps be smarter about what we're looking at as solutions. We don't always need to think of the end of pipe, build something shiny or concrete and do something. I think we can start to look at some of the other measures more. So through Workware, more recently, we've started to look at sort of control at source, so permitting options. How do we stop this stuff ever coming to us? And through regulation, we would need support on that. You know, the water companies have very limited regulatory powers back to what comes into the networks. So yeah, regulation is going to help us either by doing the source control or by, you know, providing that push for the end of pipe investment that's needed.
Thank you. Ehi, this one's kind of, I guess, related a little bit to the sort of green chemistry space that we were talking about earlier. So how accountable should producers, so both historic and current, be for reducing the harm caused or alleged by emerging contaminants and ensuring that future products are harmless while also still being effective?
I think they should be very accountable. Obviously, we're not as litigious a society as the US. And also, having come out of the EU, it becomes a bit more difficult to understand, well, what's the scope for UK and how are we going to regulate some of these chemicals? But I think it's easy to kind of maybe discuss those for industrial chemicals. However, you know, when we're looking at pharmaceuticals, it becomes a bit more challenging because we depend on chemicals in general for everyday use. But when you're talking about medicines, it becomes even more difficult. I think there's, in some ways, you know, I suppose the producers can do some degree of educating of how you dispose of medicines effectively. But, you know, disposal aside, you know, at the end of the day, those medicines are designed to be consumed and be used, and the way they're metabolized and how the body breaks it down, there is no control over that. And so it boils down to, you know, shared responsibility. Yes, the manufacturers have a responsibility, but I think we all have a responsibility, the water companies, and how they manage the waste, because that's what, you know, the public are paying for as well. And I think they will be held accountable. I'm not convinced that it falls down to just the manufacturers. Yes, there's the design aspect, but ultimately it's driven by consumer demand as well. And so that becomes really difficult.
Thank you. Andrew, there's one here asking, you know, saying that the public gets their information from the science and raise awareness to politicians and funding bodies. The public is an ally, not the problem. First of all, do you agree with that? And if so, should we be getting the public involved with the development of our call for innovation?
I think there is a need, certainly, and I don't know the answer to this, to a much better educated public about the water, about rivers and drinking water, where it comes from, where they fit in. We have an example of wanting many more houses and people concreting their drives, and you get more runoff into the sewers, which lead to more CSOs. A lot of people aren't really connected and educated as much about our water system as we would like. I think if we could influence, educate people better, maybe that might help the appreciation of what's going on. But there are some difficult actors in this. The newspapers and social media mean it's a very difficult world to succeed with that education process. I'm someone who is data driven, and I'm constantly looking for the evidence of harm in rivers, using as wide as evidence base as I can. And the more I look, the more I realize that things are actually doing rather well in rivers, and biodiversity is improving. But if I say that to the newspapers or journalists, I'm seen as a crank. But the data's all there. And I think one of the problems here is that, if there's 300,000 chemicals out there and more being produced every day, we're always behind the curve. And I think being able to manage that via the normal lab-based ecotoxicity approach, and then trying to consider risk, we're always struggling, we're always behind, which to me makes me think of, you must try and see the environment through the eyes of wildlife and actually understand how the wildlife are behaving in the environment we've put them in. Are they doing better? Are they well? Are they reproducing? Are they diverse? If they are, let's move on to where the problem is.
That makes sense. And while there are loads of other questions still in the chat, I think it's a nice place to kind of wrap up. I'll maybe just ask the panel one kind of final thing. If you have any further reflections or any kind of new thoughts that have been sparked from this conversation that we've been having this afternoon, it'd be a lovely place to share them. Ehi, I can start with you. Or any watch outs or any sort of recommendations you would give to us further than we've spoken about already.
I'd say I think what you're doing at the moment, getting input from the water industry is really important. Where they, understanding or trying to at least balance what they're finding challenging, and where the regulator is coming from, trying to actually answer the question of, is it a problem? Are these emerging concerns that we're hearing about, is it a bigger problem as we think they are? And should we be actually doing anything about it, or what should the focus? I think that is the right approach. I'm not quite sure if there's any one spark, moment or focus. I'm not sure really.
No, I appreciate that. Thank you. Does anyone else on the panel have any sort of final reflections to close off with?
I think for me, the thing is, we do want to do something. We just don't know what we need to do. And obviously, this is the whole part of this, is to try and shape that. And there's just so many different avenues we can go down, and we just need to find that breakthrough, that we'll go down one track and hope that's the right one. I don't have any answers. I'm sorry. I've just got more questions buzzing around my head now. So.
Okay. Andrew, you raised your hand briefly there.
Yeah, I'm a big one on context, Thomas, and I've got some textbooks on the wall back here, and it shows the number of rivers in 1960 which have no fish in them, none. And that was almost a quarter of rivers had no fish in them. So we've come a long way, and why is that? Well, many of the chemicals, despite our concerns that we use are more benign than they used to be. The treatment is better than it used to be. So the conditions in our rivers are far better than they were. That doesn't mean we isn't more we could achieve, but in terms of the overall picture, we're in a much better place than we were in the 1960s or 70s. Far, far better.
I'd agree that perhaps the chemicals are far more regulated than they were in the past, but I'd still argue that we need to monitor. Obviously, it depends on where you're taking your measurements from, and depending on the rivers and how diluted they are, I think, and also the timings of when you're taking those measurements. It's great what you're saying about the biodiversity not being impacted, and I'd love to believe that that's the case across the UK, but I don't know enough to say that with any certainty without having reviewing the data to back it up, and also when is that, how frequently is the monitoring being undertaken? Whereabouts are the samples being taken from? I think it would be helpful to have a more comprehensive look at the data. I would hate to kind of for the participants to kind of go away and just say it's all fine, the rivers, there's no contamination. We shouldn't really be having this conversation. I think we're far away from that. And I wouldn't be comfortable leaving this conversation to say, actually, off you go. There's no problem at all. Let's not talk. There's no need for this discussion.
Thank you, Ahi. Gemma, same option for you. If you have any final thoughts or reflections for us.
I guess I would say that I definitely agree with Ahi there, that I would not be comfortable as well to leave this conversation saying that I think we do need to be looking at more. And then it just goes back to the point I made at the start, is the monitoring that we do. I think maybe there are ways that we could change that we need to adapt to different monitoring. I think there's also a point about, it goes back to the public knowledge about it and stuff, and the pressures from the public. I think there's also an opportunity here for like citizen science projects. I think we've really touched on that at all, but I think we don't necessarily utilize them as well as we could do. And I think there are definitely opportunities out there where we could use citizen science, like from monitoring programs, to help us with data collection. And maybe that's a way to get the data that we then need to see, to be able to see actually what is our impact on the environment, and to maybe give some peace of mind to people, or not. It might not, but I think it's just to get that knowledge. And I think also with citizen science, it's quite a nice way to engage the public, and it fosters a nice community and like local stewardship of the rivers and stuff. So I think, yeah, there's definitely something in that too.
Okay, thank you so much, and yeah, thank you to the four of you. It's been a really productive and interesting conversation. I've certainly enjoyed it. I've learned a lot coming as the non-technical person, just trying to make sense of the topic area a little bit. But yeah, that's the end of our panel. Thank you to the audience for all the great questions as well. So yeah, thank you so much, folks. I will just do a couple of minutes of final wrap up just as we say goodbye, next steps and the like. So thank you very much. Let me just get my screen up. So yeah, I think like the most important thing to say before outlining next steps, going any further, is thank you. Taking a second for gratitude, I think it is very important in moments like this. This has been our second ambition surgery. We ran one at the end of January, and we've run the second one now. It's part of a continued iterative process at Spring to make sure that we are delivering value to the sector, and we really appreciate you all coming along this journey with us. Big thank you to all the speakers for giving us such an amazing deep dive into everything emerging contaminants, to Natalie for doing everything behind the scenes, Spring team, Kira Ellis working away in the background to make sure all the technology is working without any sort of major hiccups. And of course, the RSE, who are the sponsor for Spring Accelerator 4. It's been a great session, and we're looking forward to the next steps. Those next steps, we have quite a lot of work to do, I think, after these conversations today. Our plan for the call is to go live in the next 4 or 5 weeks. But before then, we need to digest, consolidate all the great information, draft our call for innovation, iterate it on top of it with our water company partners, innovation functions, subject matter experts. Alongside the call, we'll also put out, or we will share at the end, the recordings from today's session, so that either you can go back to them, reference them, or people who weren't able to attend can experience all the great content from today. We will be reaching out as well with some data gathering. We're looking to understand all the other projects that have happened in this space, so again, that we don't create duplication. So we'll reach out to everyone with a little note about that. And yeah, I think please, if you haven't followed us already on LinkedIn, all of the social stuff, you can stay up to date with all things Spring and engage with some of our other great service offerings, our showcases, read some case studies, that sort of thing. Yeah, again, thank you everyone, to speakers, and for everyone for showing up and participating today. Watch this space. We'll be hopefully launching a challenge in this space very, very soon. Thank you all so much. Have a lovely rest of the day.